new on CuriosityStream.
I'm James Burke. I'm going to take you on a journey through time.
James Burke's visionary series returns, reimagined for our time.
Now, this is all uncharted territory.
The Washington Post hails Burke as one of the most intriguing minds in the Western world. The New York Times raves he careens from one great moment in history to another.
Where do we want to go from here?
Experience all new Connections.
So what's the next connection?
With monthly, annual, and bundled plans, find the one that works for you at CuriosityStream.com.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime, Series 23, Episode 98, for broadcast on the 21st of September 2020. Coming up on SpaceTime, a special edition looking at the discovery of a potential signature for life in the clouds of Venus. What does the detection of phosphine really mean? And how excited should we really get? We'll answer all those questions and more on this special edition of SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have detected signatures for life in the form of the chemical phosphine in the clouds enshrouding the planet Venus. While the discovery of phosphine in the atmosphere of Venus doesn't mean evidence of alien life, it does raise serious questions about how it got there. The rare molecule consists of a phosphorus atom on top of 3 hydrogen atoms arranged in a pyramid. On Earth, phosphines are only produced through biological processes by anaerobic bacteria deep in oxygen-starved caves, or artificially by industry for fumigation. However, phosphines are also produced under extreme conditions in the turbulent atmospheres of the gas giants Jupiter and Saturn, using enormous amounts of energy from planet-sized upper atmosphere convective storms. The thing is, until now, it's never been detected on small rocky terrestrial planets other than through biological processes. Astronomers have speculated for decades that the high clouds on Venus could provide a home for microbes, floating free of the scorching surface, but still needing to tolerate very high levels of acidity. And the new findings reported in the journal Nature Astronomy suggest the detection could point to this extraterrestrial aerial life. The authors first detected their phosphine signatures using the James Clerk Maxwell telescope in Hawaii, and then confirmed their discovery using ALMA, the Atacama Large Millimetre Submillimetre Array Radio Telescope in Chile. The study's lead author, Professor Jane Greaves from Cardiff University, says in the beginning the experiment was one of pure curiosity, taking advantage of the James Clerk Maxwell Telescope's powerful technology to rule out extreme environments like Venus's cloud tops as possible sources of life. So getting these first hints of phosphine in Venus's spectrum was quite a shock. That's why follow-up observations using ALMA was so important. Getting the same signature, but from a different set of instruments, was crucial in ruling out some sort of a technological glitch. Now, based on this data, the models of the Venusian atmosphere suggest these phosphine levels would be extremely low, only about 20 molecules per billion. Of course, before shouting from the rooftops that they've discovered life, the authors have been running calculations to see if the phosphine could be coming from some natural processes on Venus. And they do caution that there's a lot of information about Venus which is still lacking. That means the jury's going to be out for some time, because the only other study of phosphorus on Venus came from one of the lander experiments carried out by the Soviet Vega 2 mission way back in 1985. Massachusetts Institute of Technology scientist Dr. William Baines led the work on assessing natural ways to make phosphine. The ideas included sunlight, minerals blown upwards from the surface, volcanoes, and even lightning. But none of these could make anywhere near enough phosphine to justify what they were seeing in their spectra. In fact, potential natural sources of phosphine in the Venusian atmosphere could at best only make about 1/10,000th the amount of phosphine which the authors have detected. Stirring the pot a bit further, Dr. Paul Rimmer from Cambridge University has calculated that to make the observed quantity of phosphine on Venus, terrestrial organisms would need to work at about 10% of their maximum productivity. Of course, any microbes on Venus or in the Venusian atmosphere would need to be very different from their earthen cousins in order to survive the hyperacidic conditions. Earth bacteria can absorb phosphate minerals, add some hydrogen, and ultimately expel phosphine gas. But the thing is, it costs them energy to do this, so why they do it isn't clear. Phosphine could just be a waste product, but other scientists think it could be used to ward off rival bacteria. Whatever the reason, another MIT team member, Dr. Clara Souza Silva, has been looking at the idea of searching for phosphine as a biosignature gas of non-oxygen using life on other planets, because normal chemistry makes so little of it. She says finding phosphine on Venus was an unexpected bonus, with the discovery raising lots of questions such as how any organism could survive. After all, on Earth, some microbes can cope with up to about 5% acid in their environment. But the clouds of Venus are almost entirely made of acid.
Finding signs of life on other planets beyond the Earth would be a way of answering the biggest questions that we've had as a species so far. Where do we come from? Are we alone? But of course, these questions are not the exclusive purview of scientists. People have been asking them for as long as there's any record of them being able to ask these questions. What is special about this moment and our role in it as scientists is that for the first time, we're actually able, because we have the tools, to answer these questions. Phosphine is my favorite molecule. A phosphorus atom on top and 3 hydrogens in the base of this pyramid. And phosphine is an extremely difficult molecule to make. It is only spontaneously made in extreme environments, such as what you find in the hellish depths of Jupiter and Saturn. It is otherwise only made either naturally by life on Earth or artificially by humans, as a fumigant, for example. If we have indeed found life outside the Earth, it puts our own existence into perspective. But it also tells us that life may be much more common than we first imagined. And there's a huge array of possibilities out there in the galaxy of life with different biochemistries and desires. And of course, if we have found life right next door in our planetary neighbor, that would be so cool.
Of course, there are other possible biosignatures in our solar system, like methane being discovered on Mars and water venting from the ice moons Europa and Enceladus. But remember, these are simply signposts telling scientists where to look. Doesn't mean there's life there. Still, on Venus it had previously been suggested that the dark streaks where ultraviolet light's absorbed in the clouds could come from colonies of microbes. In fact, Japan's Akatsuki spacecraft is currently mapping these dark streaks in order to better understand this unknown ultraviolet absorber. Overall, the discovery of phosphine in the Venusian atmosphere is significant because the authors can already rule out lots of alternative ways to make it. But they admit making that leap to say this means alien life is going to require a lot more work. As Carl Sagan said, extraordinary claims require extraordinary proof. MIT's Dr. Janis Bukowski says the high clouds of Venus are incredibly acidic, around 90% sulfuric acid. And that poses major issues for any microbes to survive there. There is, however, a narrow temperate band within Venus's atmosphere, between roughly 48 and 60 kilometres above the surface, where temperatures would range from 0 to 100 degrees Celsius. Scientists have previously speculated that if life exists on Venus, this layer of the atmosphere is likely to be the only place where it could survive. And Patowski says it just so happens that this cloud deck is exactly where the phosphine signal was observed.
So a group of scientists led by Jane Greaves from the University of Cardiff were looking for signs, for chemical signs on Venus that shouldn't belong there. And one of such molecules is phosphine. And they, unexpectedly, they actually were able to find a signal that belongs to this molecule. So then we raced to figure out what could be the reason for phosphine on Venus. And this is where our MIT team comes, when we actually looked at all kinds of processes, chemical and physical, that could potentially produce phosphine in Venusian environment. This is an atmosphere. The surface of the planet is completely uninhabitable. the atmosphere is the only place in which life actually could, in principle, exist. And there is a belt of clouds in the atmosphere. And we concluded that there is no known chemical and physical process that could conceivably produce phosphine. So this adds to the mystery of Venus. And then this opens a very rather bold possibility that there might be something living in the clouds of Venus. So the question is why it is actually a staggering discovery, why it is so important. Well, there are a couple of angles that you can actually answer that question with. One, the first, is that phosphine is absolutely unexpected. It cannot be produced on rocky planets. At least we don't know of any known processes, chemical or physical, that can produce phosphine, which means either our understanding of the physics and chemistry of the rocky planet is severely incomplete, or there is some chemistry that is so unbelievably weird that it could even be life.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
So where do we go from here? Well, the authors are now waiting for more telescope time in order to determine whether the phosphine's in a relatively temperate part of the clouds, and to look for other gases there that could be associated with life. As well as being Earth's nearest planetary neighbour, Venus is considered to be Earth's sister planet. After all, they're both almost the same size with similar mass and diameter, and they were formed under similar conditions and out of the same materials. In fact, Venus once excited speculation that it could host the first human colony in space. Scientists used to think Venus's dense cloud cover meant lots of rain. After all, it's closer to the sun than the Earth is, so temperatures would be a lot warmer, dare I say tropical. That would mean more water evaporation, hence more rain clouds. And so scientists envisaged that under its thick cloud cover, Earth's sister planet was covered in lush green tropical rainforests. Sort of like the Amazon jungle on steroids. Some even speculated that tropical rainforests would have meant lots of animal life, not just plants. And that allowed the imagination to take another leap and consider a primordial landscape, primitive, maybe with lots of dinosaurs roaming around the place. After all, if Martians make canals on the red planet, why couldn't there be dinosaurs on Venus? But as scientists got to really understand Earth's sister planet, they realized it's nothing at all like that. Venus might well be Earth's sister planet, but it's a twisted sister. Soviet and American probes revealed Venus to be the closest thing to hell in our solar system. It has a suffocating runaway greenhouse effect. Its surface is scorchingly hot with average temperatures of 462 degrees Celsius. That's hot enough to melt lead. And those thick, opaque planet-shrouding clouds? Well, they do cause rain, but the rain isn't water. Instead, it's droplets of metal-eating sulfuric acid. Scientists have even seen what looks like snow caps on some of Venus's tall mountain ranges. But the snow isn't frozen water, it's actually metallic. The clouds are so heavy they crush Venus's rich carbon dioxide-based atmosphere, acting like the lid of a pressure cooker, and giving the planet a surface pressure some 92 times greater than the average sea level surface pressure on Earth. The surface of Venus is dominated by hundreds upon hundreds of volcanoes, more than any other planet in the solar system. And that surface is some 90% basalt, consisting of a mosaic of volcanic lava plains. This indicates that volcanism has, and maybe still is, playing a major role in shaping the planet's surface. Venus orbits the Sun every 224.7 Earth days. It rotates in retrograde compared to most other planets in the solar system. That means the Sun rises in the west and sets in the east. But sunrise and sunset do take a while. In fact, a day on Venus lasts some 243 Earth days, meaning a Venusian day lasts longer than its year. The Soviet Union have sent numerous spacecraft to the surface of Venus, but they've all had a really tough time surviving. The first few were crushed and cooked in the Venusian atmosphere long before reaching the ground. Eventually, the Russians built a probe that did make it all the way down to the surface intact. But it wasn't able to send back much data because its equipment had melted by the time it touched down. Finally, after lots of effort, one probe did make it all the way down to the surface, surviving just long enough to send back a few precious seconds worth of data and images. What scientists saw was an eerie, parched world, bathed in a half-yellow light by the thick cloud cover. The surface is covered by jagged slabs of maroon-coloured rocks, baked over the eons to create a desertscape periodically resurfaced by volcanism. Based on the Russian experience, the Americans, the Europeans and now the Japanese have all limited their explorations of Venus to orbital missions. The adverse conditions on the Venusian surface focused planetary missions away from Venus and towards Mars, which is further away and cooler. But this new discovery of phosphine in the Venusian atmosphere is likely to bring about a change. Commenting on the discovery, Dr. Brad Tucker from the Mount Stromlo Observatory at the Australian National University says the discovery means there's a new part of Venus which scientists haven't understood until now. And determining exactly what generated the phosphine is going to be a major scientific target.
Phosphine has been the surprise, exciting announcement. Phosphine being a mixture of phosphorus and 3 hydrogen atoms. And it was detected in the Venusian atmosphere, in the upper layers of Venus's atmosphere. And this new study went through lots of processes to try and figure out what was causing this. You know, what known chemical or geophysical or any process of the planet would create this. And what they found was that the amounts that they're seeing, there wasn't a known process that could explain this creation of phosphine, which led them to say that either there's something unknown about Venus that we don't know physically, which is completely possible, or it could be a production or a byproduct of microbial life.
Because we see phosphine as a byproduct of microbial life here on Earth.
That's exactly right. You know, we can look to what we know of some not quite extremophiles or extreme types of life, but definitely different types of life. And phosphine is produced because, you know, it's not just that they've detected phosphine, but phosphine is also short-lived. It doesn't stay around for that long. So it's not like just having oxygen or just having carbon dioxide. So something relatively recently, and not recently on the normal astronomy terms of billions of years, but, you know, actually recently, must have created it or at least still be creating it. One of the things they did look at was the source of the interaction from what the sun is doing on the atmosphere, subsurface or subatmosphere activity from volcanoes or whatever the activity is going on Venus, some of the other natural photosynthesis processes and adiabatic processes and the normal like chemistry that happens on Venus. All of it, from what they assume, you know, there are a few things that can be created, but not in the relative quantities that they're saying. I think that's the key here. It's just the production levels are beyond what budgeting all these different things in they can account for.
Of course, this is all highly reminiscent of what we've been hearing about on Mars recently as well, with methane production. We haven't found any flatulent bovines on Mars yet, but the search is on.
I mean, that's exactly right. And that's the exact parallel I've been saying. It's essentially identical to Mars. Obviously, it's a different molecule. But as you said, you know, methane is produced by, as you said, famously cows, but also a different type of microbe. And I think either way, the community is just excited because, you know, Venus kind of was slightly written off in terms of the exploration. Not that it wasn't studied or understood, but there's so much attention to Mars. It's kind of like Venus saying, hey, you know, I have some interesting things going on too. And early on, we often forget that the Russians in particular sent rovers or probes to Venus to explore it. It was just quite harsh.
It's a tough place to visit, let's be honest. Spacecraft get crushed before they even reach the surface. It's been a tough gig.
It really is. And you can kind of understand where everyone's like, all right, look, we're just going to focus on Mars because it's easier. And that was fair. And as you said, the discovery of methane on Mars just made it even more exciting because either there's, you know, again, geology or physical processes or, again, potentially microbes. And here on Venus, it's clearly saying there's something else that we don't know. In particular, ignoring actually just the life question. When we think about Earth and what it means in comparison to other planets, we kind of see that we're different from Mars, we're different from Venus, but there's similarities of both we can kind of draw in our history and their history. So it's interesting just for understanding how planets form, how planets evolve, what planets have, and then thinking about that question in the broader terms of planets around other stars, exoplanets.
Of course, when we talk about Venus, we have to look at its dense cloud cover. This is where we think if there are phosphine-producing bacteria, this is where they're living. Do we have an analogue on Earth?
So, this is, I think, maybe the analog here is almost the reverse. When we think of having something at 50 to 60 kilometers in the atmosphere where the location or the source of this has been, we often forget that, the surface of Venus is terribly hot. It's 462 degrees Celsius or whatever it is. On Earth, obviously, we're quite comfortable and temperate on the surface. As we go into our atmosphere, it's dramatically cooler. At 30 to 40 kilometers, it's minus 40 to 50 degrees Celsius. So when you start at 460 degrees and you go up in the atmosphere and cool down, it gets a little bit more balmier, a little bit more palatable. So I think that, the idea is almost the reverse of what it would be like from going underneath the ocean, really the life that's there in terms of the pressure and density that the atmosphere has of Venus and the changes of temperature you get as you descend from the ocean into our own atmosphere. Astrobiologists have been looking for these extremophiles, these extreme types of life on Earth, and they found them, as he said, deep in the oceans, in caves, near volcanic vents, and high temperatures, in the vacuum of space. There's all these different things where life on Earth has been tested and been shown to survive. So it's not extreme to think that there could be something on Venus. I think then the big question is if there really is, and again, no one's saying that this is it, that it is the real question then starts to be how similar to life is it on Earth? How different to life is it on Earth? Would we recognize it as life in the sense of what we think of Earth now and know? And that's kind of this big question of the life question. Again, when this applies to Mars, we only know of one experiment, i.e. Earth, that's developed life. So it helps frame and put into picture the scientific experiment that is life on Earth and how unique or not unique we are. We sometimes try and shoehorn this definition of life into something that we can label and smack on it and just say, this is life, so let's go and find it. But it may not be that. And this thing on Venus that is a little bit different and a place we just didn't really think in modern day would have life, really just goes to show that the question of trying to understand the experiment of an evolution of life as a whole and taking that step back is quite important. It's kind of like saying we're going to study planets around other stars and all these exoplanets, but we're only going to consider things that are exactly like Earth. Well, no, that's a bit short-sighted, and now we realize there's tons and varieties of exoplanets. This could be the same thing for life.
Okay, where to next with something like this?
I think one of the interesting things here is that this was discovered using what we call submillimeter telescopes in ALMA, so a sensitive radio telescope in ALMA in Chile, and also the James Clerk Maxwell telescope in Hawaii. So you can be assured now that they've detected it, just as that methane, as you said, on Mars, there will be a lot more further study. How often does this change? Do the levels change? Does it disappear at all? Is there any correlations with season or rotation of the planet or anything or different pockets? And then it's the question of, do we send something to Venus? As we were just saying, it's a hard gig to get to Venus, but technology's come a long way. Maybe we should try it again. And if it's only into the atmosphere, maybe we don't need to send a probe to land on the surface where it's a little bit harder. Maybe we just need to send a rover or a drone or even a balloon, as some people are talking about, to the Venetian atmosphere to explore it. So I think a lot more people and Venus is going to be higher on scientists' bucket list, let's say.
That's Dr. Brad Tucker from the Mount Stromlo Observatory at the Australian National University. The detection of seasonal methane in the Martian atmosphere has been exciting astrobiologists ever since its discovery and confirmation a few years ago. But there are lots of geochemical processes which could explain the presence of methane on the red planet. And that's why Venus is so intriguing. Scientists are yet to find a non-biological explanation to explain the presence of phosphine in the Venusian atmosphere. Although ANU astronomer and astrobiologist Associate Professor Charlie Lineweaver says there are bound to be things they haven't considered.
Yes, we're all looking for life, and whenever there's a tentative signal like this, we all get excited and say, oh, have we detected life? And that's what we do in astrobiology. And it's the interest of the public that keeps a lot of this research going, because most of my scientific colleagues would make a wonderful discovery, and then the public don't care. And that's your job to understand why you should care, which ones you should care about.
When I first saw this a couple of days ago, when I received the embargoed copy of the paper, just looking at the headlines, I thought, oh, really? This is obviously something designed to get people interested during COVID-19. But as I read through it, I realized that these people actually had something here. They've eliminated everything they could.
That's right. I Bill Baines is the chemist that's working on the production of phosphine, how it's done on Earth, and how it could be done on Venus. And there are three papers here. One paper by Greaves is the one that detected the phosphine in Venus. Then there's another one by Baines who goes into more detail about why or how it can be produced and why it could not be produced abiotically. And there's a lot of uncertainties in that, but he has done, as I sometimes say to my graduate students, we don't do good science, we just do the best science. And I think that can also be described here as useful to describe what's been going on, because there are lots and lots of uncertainties, very hard things, error bars that can be very enormous, but it's the best thing it's the most detailed analysis of this gas. We're talking about parts per billion, so that's really small, about 10 or 20 parts per billion in the Venus atmosphere, and not just any part of the atmosphere, not in the polar regions and not much in the equator, but more at mid-latitude. And they also used probably the best instrument in the world for this, and that's the ALMA instrument in Chile in the Atacama Desert. So they really employed the best telescopes and some very good people to do this analysis, but there are still lots of uncertainties left. And my reaction to the paper is, oh, that's a great measurement, but what does it mean? And I don't think we know what it means. It reminds me very much of ALH 84001, the meteorite from Mars, where people looked at it very, very, very carefully and said, oh, the only thing we can come up with, it's probably life here.
It's life or crystals, one of the two.
Well, magnetite. I mean, some of my colleagues still think that there is evidence for life, but I guess what's important here is that anytime we make progress in technology and get a really good instrument like ALMA, and then look very, very carefully at the detailed high-resolution spectra for different molecules, then we find something. So what in the world is that? Hey, we found phosphine. The people who are involved in this, some of them are driven, some of the group by Sarah Seeger and Bill Baines and Clara Sousa Silva, they are at MIT, and Graves, I think, is at Cardiff. Yeah. But I should point out that the MIT group has taken a very, let's say, relativistic view of potential biosignatures. I've been looking for biosignatures like oxygen and methane and CO2 and other fairly abundant gases in atmospheres. But they've said, oh, you know what? There are hundreds and thousands of molecules that are produced by life. Let's look for all of them. So that's a very different approach to looking for biosignatures, and one in which is only useful if you look very close to, because the signal to noise has to be gigantic to find parts per billion in an atmosphere. But I was just looking through the Baines article on possible explanations of how phosphine is produced. And one of the things that's important to notice is that it is produced on Earth, but it's produced mostly by life forms. He's claiming exclusively by life forms. And phosphorus, you should know that DNA has a phosphate backbone. Phosphorus is a very important element for life. It's not one of the big four, CHON, carbon, hydrogen, oxygen, nitrogen, but it is one of the big two, the sulfur and phosphorus. And those six elements.
It wasn't all that long ago when astrobiologists almost fell over themselves when they thought they had discovered a form of life on Earth that didn't contain phosphorus.
Yeah, that was the arsenic-based life that turned out to be an inappropriate analysis.
Oops.
And well, that was a bigger mistake. If this current, they're not saying definitively that they've detected life on Venus. They're saying that we can't explain it, and that's probably the take-home message. We've detected something that we didn't expect, and we can't explain it. One explanation for people who get excited about such things, and I do to some extent, is that it might be life. But I'm not. If I were a betting man, I would bet that it's produced by water droplets being dissociated by the UV in the upper atmosphere of the 55 to about 65 kilometers above the surface of Venus, where there are water molecules. The hydrogen then is dissociated, and then it can combine with a small amount of phosphoric acid to produce the phosphine. That would be my explanation for this, but who am I? I'm not a phosphate chemist, but just looking at the analysis that they've done, I'm a little bit skeptical because of the lack of error bars on these models. Did you look at figure 5, for example? Figure 5s are hard to look at in radio, but there's a figure that says, here's the formation rate of phosphine, here's the destruction rate of phosphine abiotically, so not produced by life. And they say there's no way that the formation rate could be high enough to produce this signal, but there's no error bar on that formation rate. And so I'm skeptical about that. I don't like science results that don't have error bars. And
plus
so
or minus.
Yeah, and here they're talking about the maximum amount is bleh. And I say, well, did you include this? Did you include that? One thing they didn't include, for example, is the convection in the atmosphere going up and down. I mean, things go up and down in the atmosphere. And that's, for example, one of the reasons we can detect phosphine in the atmospheres of Jupiter and Saturn is precisely because things are transported vertically. We cannot see the layers which presumably are responsible for producing the phosphine in Jupiter and Saturn, but because of the convection going up and down in the atmosphere, that raises enough of it up in the higher atmosphere, where it's not very much, where not much of it is produced, to being able to be seen. Because when you look at a planet, you're only seeing the upper parts of its atmosphere. Right? Another issue that your listeners should be aware of, and that is this is a single line detection of this molecule. You know, most molecules have dozens and sometimes hundreds of molecular lines, and phosphine, I would imagine, has at least dozens of lines, and this is only the detection of one of them. That means that contamination is a much more serious issue, like from sulfate, SO2, SO3, SO4, and these are things that are in the atmosphere. They did do a fairly good job of modeling that, and that convinced me that they had seen phosphine. So it's not that easy to see, and I think they did an excellent job. Even though it is a single line detection, I think they did a sufficiently good enough job to have a convincing detection of phosphine. What that means is another issue for life.
How excited are you about this paper?
Well, it reminds me very much of being excited about the searches for SETI and Christopher Columbus. Now, Christopher Columbus made a gigantic mistake, but he made a tremendous discovery because he had made this mistake. When I go to SETI conferences, they're all motivated by saying, oh, there's going to be intelligent life out there. I think there is an intelligent life out there, but because they are searching for in a new parameter space with new instruments, they're going to find something wonderful. So I'm all supporting SETI, but I'm all against the motivation. So here again, I'm all for looking for molecules and weird things in the atmospheres of planets, but I'm not all for I'm not behind, I don't share the motivation of, hey, we're going to find life, we're going to find life, we're going to find life. That's what makes it exciting. For me, what makes it exciting is looking in new parameter space, finding new molecules, and let the data talk to tell us what it is we've found rather than our expectation.
Don't frame the thing, just do it for the blue sky.
Well, yeah, the problem is that people, like, for example, Bridenstine, the head of NASA, just said, okay, now we're going to Venus because of the excitement. And I'm saying, okay, if you need excitement to do, I mean, maybe maybe Christopher Columbus needed to make that mistake in order to convince his sailors, because if he had had the right diameter of the Earth, I don't know if any sailors would have gotten on the boat, because they would have all died if North and South America had not been in the way, I think.
No matter what they find right now, the attention will be elsewhere in the United States at the moment. I think Congress are far too busy with their crosshairs pointed at each other.
You're right, but the whole point in astrobiology, everybody's looking for biosignature gases, because these are the gases, these are the things that we'll be able to detect in the atmospheres of Earth-like planets, and we need to know a lot more about how gases, or planetary photochemistry, for example, atmospheric gases at very, very low levels, and to what extent that shows you that life is there. That is really a new field, but it is one that's exploding like crazy, and this is one nice step in the evolution of our understanding of, hey, how do you detect parts per billion level gases and in other atmospheres of other planets, and what do they mean?
That's Associate Professor Charlie Lineweaver from the Australian National University. And this is SpaceTime. I'm Stuart Gary. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from spacetimewithstuartgary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through spacetimewithstuartgary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.